Now that we walk through the implementation of the algorithm by looking at some diagrams that hopefully were useful, let's talk a little bit about the data definitions and actually give the implementation for the Travel Salesman algorithm. So here we have in the module section the random library, which is going to allow us to randomize the parameter that represents the sequence in which the cities are given. The first thing that we're going to need to implement is a parameter that represents how many iterations we're going to try to find the best score so far. Then we're going to go straight into the matrix of distances. Here you can see the structure. It is a two-dimensional structure. It's a two-dimensional array where every single row represents one city. It is ordered alphabetically, going from the first row at index 0, 1, 2, and 3 as A, B, C, and D. Inside of each of the arrays, you are going to have some columns where each column, based on their index, also represents the identity of a destination city. The rows are the current city we're looking at, and the columns are going to represent the destination cities. And the values represented in those coordinates of row and column stand for the particular distance between those cities. Then we're going to have the candidate order of travel. This one is simply an array of indexes. Notice that they are all integers. They span from 0 to the total number of cities we have minus 1, because we start counting at 0. This is going to be one of the hearts of our program, because it's going to allow us to traverse and find different sequences of cities by randomly shuffling COT. Then we move to the best score. The best score is a global variable that is going to keep track on what is the minimum score we have found so far, which is the one that answers the question, what is the closest route that the travel salesman can take, or what is the most economic route. So we're looking for the smallest value. Because we're looking for the smallest value, we're going to filter every time that we find a score to see if that new score is smaller than the best score so far. So the best score should start really big. We have two options. We could simply set the BSC to a really big value like 10,000. Or something else that I like to do is to use this least comprehension to basically add up all of the distances in the matrix of distances. Finally, we have a last data definition, which is going to be a sequence of integers that represents the same type of information as the candidate order of travel. However, this one is going to be the best one found globally, which is the equivalent of what BSC is to a score. Now that we have the data definitions, it's time to move into the implementation. The first thing we're going to try to do is to evaluate one single cycle on the process of identifying the distance travel given a candidate order of travel. For that, we're going to use a for loop. The identity of the loop variable is not that important, so I'm going to keep it with the letter I for I in range, and we're going to iterate over every single number from 0 to the total number of items in the list COT minus 1. And the reason why we do the minus 1 is because of the next step. We are going to take our score, which is a variable we haven't defined yet. We're going to put it right here. And it's going to start at 0. A score is an accumulator. As we move along the matrix of distances, we're going to be adding values to the score, depending on what row and column of that matrix of distances we pick at a certain time. So here we're going to add to it we're going to add to the score the matrix of distances at the position that belongs to I, which is this index, as a value inside of this list COT. We cannot use only the letter I, because no matter what the identity of the array COT is going to be, or what the order of the components are, I will always go from 0 to 3. In this particular case, because we have 4 cities. So what we need to do instead is to refer to the index indicated at that position I for the list COT. We say COT at index I. Then this is going to be the identity of the current city. we need to identify the destination city, and that one is given by the position at COT at index I plus 1, which is the reason why we picked -1 in here, so that we are always within the boundaries of our array. Once we are done with this process, we can add one last time one of the values in the matrix of distances, that one belonging to the very last item, the very last row, which is the current city, going back to the very first item, which is the very first city where we came from. So here we are gonna say MD, and we're really just gonna copy this. We're gonna paste it here. But this one is gonna be -1. Remember that Python uses negative indexes as taking elements from the left of the very first item in the list, wrapping it around itself, wrapping the list around itself, so it takes values from the last item in the list. Another way to look at this is to say something like the length of COT -1. And because Pythonistas are very pragmatic, so we just leave it at -1. The second part is gonna be 0, which takes us back to the first city where we started traveling. That's gonna give us a score. So let's just print it out. Let's print this score and let's see what's that about. Okay, so here we are. You can see it in the interactive window that appears here on the right. The value is 48, which makes sense. If we look at the image with the diagram of the distances for these cities, you can see that from A to B is 16. From B to C is 20, plus 16 is 36. From C to D is 36 plus 7, which is 43. And from D to A is gonna be 48. So from A to B, B to C, C to D, and D to A, going back to the original city. And that is exactly what the sequence COT is. You can see it right here. The information that provides this identity is given by the order of the rows and also the columns, because it's a symmetrical matrix. Is the identity of the rows that we have here in the matrix of distances, and it gets mapped by using a helper function that we haven't developed yet. So let's work on that helper function. Let's just print out the root. So let's call this the string of cities, and it's gonna be an empty string at the beginning. The purpose of this next for loop is to populate it, is to fill it in. So for every single index in the list COT, we add to the string of cities what comes out of the call of a function called getCityByIndex. This getCityByIndex is going to receive the index, and then it's going to map it to the letter of one of the cities. We don't have this function yet, but we're going to generate it in just a second. Just like we did with the score, we're going to need to repeat this process, but this time by adding the getByIndex of the position COT at index 0. Let's create this helper function. This helper function is very simple to make. It simply represents the series of if-else statements that are going to map one particular index with one particular letter. So if the index is 0, then we return A. And through the magic of video editing, I'm gonna give you the other ones. And here we are. Okay, so now we are returning a particular letter. Just with the intention of being fancy, I'm gonna add to the string just a dash so that we can see a clearer separation between the two different letters. And then let's just print the string of cities. Let's just print the string of cities. And if our predictions are correct, well, we should have the sequence A, B, C, D going back to A, and that's exactly what we have. You can see it right here. So now that we know how to generate one cycle of the Travel Salesman problem, it's time to work on the iteration step. Here we involve the use of a better score and a better COT, which are going to be those that map to the best versions of these iterations found so far. The first thing that we need to do is to move this string of cities down below, because these ones are only going to happen once. The second thing we're going to do is to shuffle. Before the score, we are going to make sure that we use random shuffle, which is a method that receives an object, an iterator-like object, and it makes changes in place to that iterator. That means that we don't need to save it in a variable like this. It is automatically recycling the variable name. Okay, so now that we have this, we need to run this for as many items we have in the iterator, in the iterations. And this goes inside. So now we are shuffling. Then we are getting the score as a local variable, which is an accumulator. And then at the end, we can ask if the best score so far is bigger than the score that we calculated in this step. And if the answer is yes, it means that we have found a better score. So the best score becomes a score. And the best COT, which is this data definition that exists right here, is going to become COT. So best COT equals the new value of COT. However, notice that COT is a variable that keeps getting recycled, which means that it keeps its identity in the memory of in the computer memory. So what I need to do is to clone it, is to clone a version of COT and that means that this COT with the list methods wrapped around it is not gonna be the same object as this COT anymore. It contains the exact same elements, but it occupies different bytes of information inside of the memory of the computer. Okay, so now with this, we can simply go down here, and instead of iterating over COT, we iterate over best COT. And down here, we don't print the score, but the best score. Let's run this program and let's see what happens. Oops, I got an error that says integer object is not iterable. And the reason why is because here I forgot to wrap this inside of the method range, because iterations is just a scalar. It has to be a generator. Okay, so here we have the different components. So we have a score that is 45, and the order of the cities that yield that minimum score is B to D, D to C, C to A, and back to B. Rather than, if we go to the image and we take some time to look into it, we'll see that this is indeed the value of 45. B to D, which is 9, D to C, which is 7, so that's 16, C to A, which is 13, that's 29, and A to B, which is 16, giving us 45. Did we just get lucky? Is there another option out there? Maybe. With a number of iterations of 10,000 isn't very probable. But as the number of possible cities increases, the chances that we are missing the global minimum get higher. Remember that this system is based on factorials. So at some point, we're going to have more possible solutions than the number of atoms in the known universe. But what is interesting about this algorithm and a demonstration on why heuristics work so well is because we don't really care about the global minimum. We just want a good enough approximation, something that has an application. Let's run this a couple more times. And every time the value of the score is 45. Notice, however, that it is not just one root. It is multiple roots that yield that minimum score. And that is the Travel Salesman problem.